We're going to do 10.3 today. That'll wrap up chapter 10. That means Thursday we'll do a review day since it's been a minute since we've probably thought about differential calculus. And then we'll do the test on the following Monday. That test covers 9 and 10 though, remember? Not a big deal because all the things you learned in 9 are just the tools we're still using to do problems in 10. Like 9 was like the tools and 10 is like the applications. So it's not like bonkers to combine the two together. We'll have one more chapter to do after that, doing integral calculus. And then we'll kind of see where we're at with days left in the school year to figure out what to do after that. Cool? Yeah. So in 10.3, we're going to be looking to solve what are called optimization problems. So like, say you wanted to build like your optimal sized pop can, right? So your optimal sized pop can is going to contain the most amount of soda using the least amount of material, right? That'll create the best possible container for you as a company. Everybody's okay with that? So the question here becomes like, okay, how do we do this kind of optimization process? How do we find like what's the cheapest way or the best way or to do this? Like, how do I do something using the least amount of stuff? Or how do I do something getting the most amount out of it, right? Those are usually your two types of optimizations, are mins and maxes. So we can do this using calculus. Let's do an example here to kind of illustrate that. So let me drop this in here. And then it says there's a picture. Oops. All right. Oops. All right. So let's look at a specific example here. It says the dimensions of a piece of A4 paper, that's like your standard sheet of paper, to the nearest centimeter are 21 by 30 centimeters. It's possible to create an open box by cutting out square corners and folding the remaining flaps up as shown in figure 10.10. So that's the picture here along the side, right? Here's my box, or my paper. I'm going to cut these squares out like we did here, and then fold up the sides to make my open top box. We want to calculate the maximum volume of the box and then find the dimensions of the open box that contain that largest possible volume, again, using this method that we've shown here. All right. So to do this, what we're going to want to do is start by kind of trying to choose an appropriate model to describe what's going on here. So I need a function that's going to describe the volume for this box. So anybody remember from geometry, how do I calculate the volume of a box? Length times width times height. Don't worry about memorizing that. It would occur on your equation sheet on your IB exam. We're on your test. Now, what's the problem with this formula as we've written it? If I have a function that I want to do calculus on, it really needs to be y equals something in terms of x, right? I need two variables, right? An independent, dependent variable. Right now, how many variables does this equation have? 4. So my first order of business is going to be to try to resolve this into a two-variable function that I can use calculus on. So I'm going to go ahead and look at my picture here. So like length, width, and height for my box, right? Everybody's cool with how I've labeled that? So if I go to my picture then, that spot's the width, that spot's the length, and like that spot there is like our height. Everybody agree? Still feeling good? Okay. So if I go back here, we're told that our box is 21 by 30. So I know that's 21. And I know that's 30. So what I'm going to do now is I'm going to try to rewrite my values for length, width, and height in terms of x. So this spot right here is my length, right? So is that length going to be, it's related to 30, right? Is it bigger than 30 or less than 30? Less than 30, right? Because we can see there's two pieces missing. What two pieces are missing? How long are those two pieces? They're x each, right? Each of them are an x long. Everybody agree with that? So L can be 30 minus 2x. Everybody's good with that? Now, this side here is our width. That side is clearly related to the 21. Is it bigger than 21 or less than 21? Less than. So we're going to be subtracting from 21. How much should we be subtracting from 21? 2x. And then like this spot right here is our height. What is our height? Just x. Everybody feel good with what we've done there? So we can say volume now is 30 minus 2x times 21 minus 2x times x. Length times width times height. What I'm going to do now, if I'm going to use calculus on this, if I'm going to take a derivative, what is this thing going to have to look like? Am I going to have to do this? Because can I take a derivative of this the way it's currently written? We don't know how to do that. So what are we going to have to do to this to get it into a spot where I can take the derivative? Well, not factor, the other F word. FOIL, or distribute. Yes. So let's multiply this whole thing out, right? So when I do that, I'm going to just do that quickly in my head. Is that okay? Okay. All right. So this is an equation for volume in terms of x. Remind me, what am I looking for in this equation? Maximum volume. Where does a maximum for a function occur? It's where the derivative is equal to 0. Okay? So to find this maximum, or potential, I guess I should say, a maximum or minimum can occur where the derivative is equal to 0. We don't know exactly if it's going to be a max or min right off the bat, but we need a derivative. So to take the derivative of velocity, or the volume here, what's the derivative of 4x cubed? 12x squared, excellent. And the derivative of negative 102x squared? Negative 204x. And the derivative of 630x? 630. And now we're going to be interested where that derivative is equal to 0. That'll give us the extrema, the maxes or mins. To solve this equation equal to 0, what could I do? You could use the quadratic formula. Good. What else? You could try to factor it. You can graph it on your calculator and look for the x-intercepts. That's what I would recommend for us because there's no formula to memorize and it's pretty darn fast. So if you have your graphing calculator with you and you want to follow along as we review how to do that, I invite you to take that out and follow along. If you're like, yo, I just want to kind of sit and watch, that's totally cool. I'm going to just delete some stuff out of here. Okay. So I'm going to press the y equals button. I'm going to type in my derivative. And then I'm going to hit, I'm going to go pick a window here, right? So let's try to be smart about this because we want to be able to see the entire graph. So x is representing that the size of the square that we're cutting out, right? So that x value, can that be negative? No, right? It's a length. So let's set the x-min to be 0. What's the biggest x that we could possibly cut? Be 10.5. Why 10.5? Yeah, because if I pick anything bigger than 10.5, I don't have enough of 21, right? That's the shortest side. So 10.5 could be my biggest x. Let's just go up to 10.5 then. And then going that by ones is fine. Again, the y is our volume. Again, the smallest volume we can have is 0. The biggest volume, I don't know what I'd expect here, but I'm going to pick like, I don't know, like 200 or something. I don't really know. I'm just kind of guessing. All right, and let's hit graph. Okay. Now, I'm actually going to, oh, yeah, I'm so sorry. We're graphing the derivative, right? So the volume there, certainly, so the y is not v, it's like dv dt, or dv dx, I should say. It's like the rate in which the volume is changing with x. Now that could be negative. So that's my fault there. So let's make that possibly negative also. There we go. So it looks like we're starting to turn back here. So this value I'm particularly interested in, right? So let's do 0. So I press second in the trace button. I'm going to pick the 0 command. And now I need a left bound. So I'm going to move my cursor on the left side of that 0. Press enter. Now it asks for a right bound. Move my cursor on the right side of the 0. Press enter. And then a guess doesn't matter as long as it's in between your two bounds. And I get 4.06. And I notice that what's happening to the derivative before 4.06, is that derivative positive or negative? It's positive because it's above the x-axis, right? And then after 4.06, it's negative. Everybody see that? So what does that mean then? So it was increasing because the derivative was positive, so it gets to 4.06, and then it turns decreasing, right? Because the derivative is then negative. That means this is a local maximum. Everybody feel okay there? And I can see that that is the only feasible value for x. So this is what I want. This is actually answering part B for me right now. What's going to be my answer for part A is going to be plugging this in to my volume equation. What's up? Oh, because it wants volume, right? And the derivative of the y-coordinate is the derivative of volume, right? Part A is asking for the maximum volume. That is the original equation. What's up? The other x value, you mean the 12 or whatever? Because we observed here that the biggest x you could possibly have is the 10.5. So the 12 is a nonsense answer. It's not feasibly possible to cut in, like have x be that big, because it would mean that you'd have like negative side length of some, your width is 0 or negative or some nonsense thing. Is that's okay? Okay. So I get 1,144 point, well, I guess probably to 3 sig fig, so let's just call it 1,400 or 1,140. And then this is cubic centimeters. And then part B asks us for find the dimensions of the open box. Well, I remember that h is equal to x, so that's 4.06. Width is 21 minus 2x, so that's 21 minus 2 times 4.06, which is 12.9. And then length was 30 minus 2x, which is 30 minus 2 times 4.06, which was like 21.9. Does that feel okay there on what we did? Let's do another. Two vertical posts with the heights of 7 meters and 13 meters are secured by a rope going from the top of one post to a point on the ground between the two posts, and then to the top of the other post. The distance between the two posts is 25 meters. How far from the base of the shorter post should the rope be anchored to the ground in order to minimize the length of rope needed? And then what is that minimum length of rope? So here's my picture. I have two posts, one 13 meters, one 7 meters. I have a piece of rope that goes in between the two posts. Some anchor point, I'm going to call that R. And then goes back up to the taller post. Everybody's okay with that? So what I need to do now is write in some labels here, right? We're trying to minimize that length of rope. Now, what can we infer about the relationships of these posts to the ground? Yeah, they're perpendicular to the ground, right? That's something you're free to assume anytime you have something standing straight up on the ground. It's that those are right angles. So I'm going to call this length from Q to R, I'm going to call it X. What does that mean that the length from R to S has to be? 25 minus X. Everybody agree with that? I guess I should say, since I notice these are right triangles, I'm going to be interested in the side lengths of the the two triangles, right? So I'm going to try to label the side lengths here. We already know that the heights of those triangles are 7 and 13 respectively. We've now defined the base of those triangles in terms of X. What I want now is to define the hypotenuse of those triangles in terms of X as well. So for the sake of argument, I'm going to call this one M and N. So I know that M squared is equal to 7 squared plus X squared, or that M is the square root of 49 plus X squared. And that N squared is 13 squared plus 25 minus X squared, or that N is the square root of 169 plus 25 minus X squared. I'm not going to FOIL that out right now because I'm not sure if I need to do that or not yet. I'm just going to kind of wait on that. So that was N. So, what is my length of rope then? M plus N, right? Which is the square root of 49 plus X squared plus square root 169 plus 25 minus X squared. If I want to find the minimum for this, what do I need to do? I need to take the derivative and set it equal to 0 and solve, right? Do you know how to take the derivative of the square root of 49 plus X squared? No, you do not, is the answer. No, you do not. You have to use something called the chain rule, which is not something that you're going to be expected to do. So how am I going to do it then? It's going to just be done on my calculator. So let's show you how to get this into our calculator. Into the y equals. In the y1 spot, I'm going to press the math button. And I'm going to scroll down and pick the n derive. So I have y1 equals, and then this is all the output from just picking n derive from the math menu. N derive is short for the derivative. So here at the bottom, we're going to type in an x. We're always going to put an x there because we're always going to define our function in terms of x's. Now I'm going to type in my m plus n. So I'm going to do square root 49 plus x squared. And then get outside of my radical, type my plus sign, do a new radical, and do 169 plus 25 minus x, and then quantity squared. And then there's one more spot I have to fill in. At the very end, it has x equals 2, and I think I just can type an x there. And if I do that, I think I can graph. So what did I really do? I just took the derivative. I typed in the function I'm taking the derivative of. And at the end where it says x equals, I just put an x there, right? So it's a complicated looking function that we're taking the derivative of. But whatever, let our calculator worry about it. So let's hit graph and see what we get here. Is this going to do it for me? I'm a little scared right now. Oh boy, that didn't do nothing for me, huh? Oh. I think I have to be in radian mode for this to work. Let's try that.
Mine was the window. So
Yours was the window.
I just had to zoom fit.
Oh, okay. I guess maybe it's too small for me to see. Let's see what we get. Gotcha, okay.
What is yours? Mine does not look
I think she likes it. Oh, mine's just like more to
oh, yours is half.
So the zoom fit, the calculator is going to make some decisions based on like what your current window already was.
Okay.
So like you could end up with a slightly different looking window if you use the zoom fit, but that worked. That was a good choice there, Isaac. So I'm going to do second trace, 0 command. So left bound, that's fine right where it is. Right bound. Now this is, I want to show you guys here. So that where the cross is going to be like covered by this equation. Guys, just hold it on for a minute. Covered by the equation here, right? So I won't exactly be able to see, but I will be able to tell by just looking at the y value here. I'm just going to wait for that to go positive, and then I'll know I'm on the other side of the 0. Because otherwise I'd have to like monkey with my window again. I don't really want to have to do that if I don't. Look, it just turned positive, so that's going to be good enough. I'll press stop, press enter. And what do we get here? 875. And if I draw my little sign diagram here, before 875, L prime is negative. After 875, L prime is positive, just from looking at our graph, right? Everybody's cool with that? So I can see that we're decreasing until we get to like 875. And then we're going to be increasing after that. So this is a minimum. Everybody's cool with how I figured that out? And I like to draw the picture rather than just trying to memorize, because the picture, I typically won't screw that up. All right. So our answer is then this point, our anchor point, should be 8.75 meters from the shorter of the two posts. Everybody's cool with that? Part B then says find that length of rope. So all I need to do then is to plug that 875 back into our equation for L. So to do that, I'm going to do square root of 49 plus 8.75 squared. And then get out from under my radical, do a plus sign, and make a new radical. 169 plus 25 minus 8.75 quantity squared. And I hate doing it this way, and I'm going to show you a different way to do it in just a second that maybe makes life easier. So I get about 32.0 meters. So that right there that I had to do kind of El Stinko'd, right? So this is the way I would have, in hindsight, the way I'm going to redo this problem on my calculator to make it a little less tedious. You guys ready to watch? So into Y1, I'm going to type in that, into Y1, I'm going to type in my equation for L. So that's my equation for L inside Y1. Into Y2, I'm going to type math, nderive. Now, instead of typing that all over again, I'm going to just type Y1 here. So I'm going to press vars, yvars, function Y1, and then do X. And I'm going to just double check real quick that it'll let me do that. I assume it will let me use Y1 there, but I want to check. Yes, it's working. That's great. I'm going to just going to exit out of here then. Oops. Oh, come on now. All right, fine. I thought I could get it to stop and just exit out, but that still worked. Good. That's what I wanted it to. Now here's the bonus. So I get that 875 the same way. Now I can just do vars, yvars, y1 of 875. I don't have to do all that annoying typing. I don't have to have the one equation nested inside of the derivative. I can just do equation, derivative of y1, and then y1 of that answer. And that cleans up the calculator piece a little bit for me, right? Does that feel okay? You guys get what I was trying to do there, why that helps?
Yeah.
And that feels a little easier now, right? Or a little cleaner anyways, where you can look at it all at once. Okay. All right, how are we feeling on these? This is usually not trivial. This is not an easy kind of problem to do. So if it still kind of feels difficult, that's okay. I will tell you this, the setup is typically the hardest part for students. Once you've got the equations, doing the calculus and finding the values and all that stuff is usually not so bad. The hardest part is getting that starting equation set up the way we need it. Let's do another one and see how that goes. Says to manufacture video game consoles requires cost per day in US dollars. A factory is or in a factory capable of producing up to 1,000 units per day, you have $1,580 of fixed costs, $120 per console for production cost. Equipment and maintenance costs vary directly with the square of the number of consoles produced. Part A says, given that equipment maintenance costs are $11 to produce 10 consoles, find an expression for the equipment maintenance cost in terms of the number of consoles produced X. Okay. So it says equipment maintenance costs vary directly with the square of the number of things produced. So we don't know what that number is, but very directly just means it's going to be multiplied. And the square of the consoles produced, well, tells us to use X for that, so X squared. Everybody feels okay with that? Set up so far? Now what we're going to do is going to solve for K using the fact that when the cost is 11, we produced 10 consoles. $10 squared is 100, and 11 divided by 100 is 0.11. Everybody's okay there? So part B then says to find an expression for the total cost for manufacturing X consoles per day. So how much is our fixed cost? $1,580. And there's no variable attached to that because that's always the same. That's like your rent or your labor, whatever. Well, rent probably, because that doesn't change with how many things you make, right? Your rent is your rent. Okay. And then we have $120 per console, right? And then we have these equipment costs that we just figured out. So that's that KX squared. Everybody's okay there? And I would include a domain with this. So what should be the domain for X? Yeah. Does everybody feel good there? All right. Part C says, show that the total manufacturing cost per day increases as production increases for all X. How do we do that? Great. And what in there told you that you need to use the derivative? Really, the per day piece is now talking about a rate. Whenever I hear rate, I think derivative. Okay. So what's the derivative of C going to be? What's the derivative of 1580? 0. And then the derivative of 120, x, is 120. And derivative of 0.11 x squared. Okay. So that's my derivative. Now, increasing, we need that to be positive, right? Look at my function. What type of function is C prime? It's a linear function. Excellent. How could you tell it's a linear function? Looks like mx plus b, right? What is the slope of this linear function? 0.22, which in our case, what we really care about is it's positive. And what is the starting value for this linear function? 120. Can this ever be negative? No, right? So let's write our explanation. We have that C prime of x, which is this, is greater than 0 because this is a linear function with positive slope and y-intercept greater than 0. So this will always give us a positive value, correct? I'd say that's good enough. Now I want to be clear here for a moment. That explanation really only works if we state our domain here, right? If you didn't state your domain when we wrote our function for C of x, you would need to wrap that into your explanation of how you know C of x is, or C prime of x is always positive. Because it's really only positive over that domain, right? If x was negative 15,000, well, C prime could be negative. But that's not inside the domain for C, so it doesn't matter. Do you guys see that little wrinkle there in terms of an explanation? So you just have to be careful there that you're being thorough enough. It says the average cost per game console is given by the function C bar of x. Find an expression for C bar of x. How do you calculate the average of something? You take 5 tests. How do you calculate the average of your test score? Add them up and divide it by 5. So the average cost is going to be add up all your costs and divide by the number of consoles, right? So that's just going to be C of x divided by x, right? Now you could write out what C of x is. You could write, 1580 plus 120x plus 0.11x squared instead of just writing C of x. That would be fine. That's probably what they would put in the answer key in the back of the book. I don't think you need to do that. I think C of x over x is fine. Plus, that's way less writing, and I love that. It then says to find the minimum average cost and the number of video game consoles that should be manufactured to minimize the average manufacturing cost. So what are we going to need? We're going to need to look at where the derivative of that average cost is equal to 0. Do we know how to take the derivative of a fraction where we have x's in both the numerator and denominator? Depends is the answer. Depends. In this case, we could. Right? So let's just kind of illustrate how we can do that in this case and talk about where that would become a problem. In this case, since the denominator is a monomial, we can just break this up into 3 fractions that all have the same common denominator. This first fraction we can write with just a negative exponent. The second fraction we can reduce, and the third fraction we can reduce, right? Can I take the derivative of this? Yes, I can. If this was x minus 1 here, am I going to be able to take the derivative of that? No, you will not. Can you? Well, people can. You can't. They would not expect you to. In the case of that, you would expressly just use your calculator to do it. In fact, that's what I would probably do for this problem in general, is just use my calculator. But I wanted to show you that we can do this by hand and how to do it by hand, because we had a problem very similar to this on the last quiz, right? I just wanted to run through that as a nice review. All right, so I'm going to start this kind of the same way that I did before. I'm going to do y1 is going to be my c of x. X squared. And my y2 is going to be my c bar. So that's going to be y1 over x. And then the last thing I'm going to be interested in is then the derivative of y2. And I'm going to go back and turn off the graphs for those first 2 things because I don't really want to see those. I'm really only interested in where that average cost, or the derivative of the average cost, is equal to 0. Everybody feel good there on what I did? All right, I'm going to zoom fit this and see what I get. Oh, it's thinking hard here. Oh, I don't like that it picked what it picked here. I think is going to be a problem. Yeah, look at what I got from my zoom fit. That's pretty dumb. So I'm going to do 0 to 1,000 because that was the domain for C that we picked earlier, right? And then, I don't know, I'm going to just do like -5 to 5 or something because I don't think that average cost, that's like a cost per console or whatever. I don't think that should be very big given the relative production costs. So it looks like it's crossing just one time there, but it's really hard to tell because I'm so close to the x-axis. I think I'm going to go back and make this like 0.5 here at the top. Whew, that is close. All right, so it looks like it's just crossing that one time there. I'm pretty convinced. You guys buy that?
Oh, yeah.
All right. So 0, I need to go and find a negative y. So I'm going to do that. Just going to keep pressing left until I find it going negative. There we go. That'll do. Press enter. Go back right until it goes positive. That'll do. Press enter. Enter on the guess. So I get about, well, let's call that 120. It's not quite 3 sig figs writing as 120. I don't know if you want to call it 119.8 or something, I guess. More sig figs is probably better than too few. I noticed that the derivative was negative prior to that, positive after, which again means that's a local min. So that is what we want. So that's our number of consoles. And then it wants the average manufacturing cost for that, so that was our y2. So I got 146, and I would probably do 2 decimal places there. Since it's money, I'd probably give dollars and cents there as my rounding. And maybe the previous one, maybe you round that up to the nearest whole number since it's a console. Like you can't make 0.8 of a console. Maybe we call that 120. But does that feel okay? We got more examples. You want to see more, or you feel like you're exampled out? You wanted me to put the next one up there and let you guys try it?
Yeah.
And then let's go through it afterwards? Let's do that. That'd be a good idea. You're like, oh, Mr. Kulik, you're killing me. That is expressly what I am trying to do.
It's hard to get back.
I know, man. Let me just make that a little bigger. Yes. Okay.
Okay, guys. Pull your calculator.
Yeah, you'll probably need your calculator.
No cheating, guys.
Can I say one thing here before you guys dig too far into this? Pay attention to the units because they suck in this problem. Is you gotta be real careful because like it's seconds and kilometers and meters and minutes and like oh you have some unit mixing going on here that's just like kind of irritating. Just want to point that out to you before you get too deep in. You guys need a hint?
Oh, that's what she said.
Did that help?
You got me that time. That was their answer.
So your function for the time it takes is going to be your time it takes to run to this point X and the time it takes to swim from point X to point S, right? Right? So this is going to be the TR, and that's like our TS. Well, we haven't picked. So, yeah, so this is seconds and this is meters here. So let's write everything in meters and seconds. What do you think? Oh, no, this is not seconds up here, dum-dum. That's meters. But I'm going to do everything in seconds, probably. So we go X meters at 1,000 meters per 210 seconds. Which is just like 21x over 100. TS is going to be square root of 300 minus x squared plus 50 squared. That's the distance you're traveling per 100 meters in 60 seconds. Well, that's like 3/5 square root 300 minus x squared plus 50 squared. And now you're going to be concerned where t prime of x is equal to 0. What's up? You could have elected to do this in minutes also. should get about 281 meters. That's going to be about 91.1 seconds. So, you guys, anybody have a dog? Ever play fetch with your dog by like the beach, where you throw the ball out into the water? You know what the dog does? Well, it does this. It runs along the beach for a while and then jumps in the water and swims. It doesn't run the whole way and then swim straight. It doesn't jump right in and start swimming. If you actually like did the optimization problem, the dog is usually pretty close to the optimal. And this happens like kind of all the time in the animal world. That somehow hardwired in our animal DNA brain is like a pretty good heuristic for like solving these kind of optimization problems. Like if you look at, you know, like a bee that's like going and visiting a bunch of flowers, if you look at like you graph this as a problem, the bee almost always takes the shortest possible route between the flowers, or something really darn close to the shortest possible. It's very strange. Somehow the animal kingdom is really good at this optimization thing. Maybe not like exact, but as a really good approximate solution, which is kind of interesting.
So the setup is really the hardest.
What?
The setup is the hardest.
The setup is by far the hardest piece of this, yeah. The good news is that on the IB exams, typically the way a problem like this would go is it would be like, show that, you know, the time it takes to get from here to here is this, and then show that the time to get from here to here is this. So even if you couldn't do those two parts, it gives you the time function for you to be able to do everything afterwards. You know what I'm saying? So like on the IB exam, it's really important if you get to a problem, you're like, I don't know how to set this up. Don't punt on it, because it's almost always going to give you the setup in the problem, so you can still do the parts later on. If you can't do the setup and you can just do the follow through, you can still get most of your points from the problem, which is, if you care about your IB exam grade, which I think a few of us are diploma program students, it's very nice to know that, like, okay, even if I run into a very difficult optimization problem on the exam, I still should be able to do the parts. Like, even if I can't do the setup, I don't feel good about that, I can still finish the problem and get a lot of points out of this, even if I couldn't get some of the setup stuff. You know what I mean? So keep that in mind. All right, let's stop here. So you guys should do 10.3. There's 14 of these guys. Should try to look at these. Next class, we're going to just do the review, basically. So if you want to look at the review, and if there's stuff that you're like in particular, you know, you want us to do, let me come with those things already kind of highlighted. Or if it just turns into like, I want to do a bunch of stuff from 10.3, we can certainly do that. But that's the plan for next class, is to just get ready for the test. What's up, GF? I think I set that up before break, that I did a couple of droppies in there. Let me double check. Let me look at what
Wait, so what are you dropping?
Maybe I haven't put it in yet. Let me look real quick. As a separate announcement, though. Yeah, I haven't put any drops in yet, but according to the the syllabus. We drop a low homework and we drop a low quiz and we double a high test score. Haven't done any of that stuff yet. Basically, because we still have a quiz to do. We're going to do one for chapter 11. We still have another test to do past this one, so I wasn't going to worry about any of that stuff until chapter 11 kind of gets closed out, because I think that'll be the last assessments for the year will come from that chapter 11. My separate announcement, though, tomorrow is the IBAP registration meeting during community time in the library. You should report directly to the library. Don't go to CT first, just go straight to the library. I won't have a chance to remind you tomorrow, but I put an announcement on the My Notre Dame about it. Not that I put it in there before spring break, so you probably long since forgot about it. But they make an announcement every day during community time, but I don't assume anybody's actually listening to the announcements. So I'm going to say it here today, just as a reminder. What do you guys think? So still to do this year, we're going to do this chapter 9 and 10 test, right? We're going to do chapter 11. There'll be a quiz and a test for that. That'll be the last assessments. I might do a little bit of other stuff that's like previous learning that is still going to be on the IB exam, like a little bit of triggy stuff or like geometry-ish stuff. It's not going to be bad. It's not going to be bad. It's going to be relatively easy things. And I'll get you guys a practice IB exam. I can get you the one from last year and an answer key for it, so you have something to look over. In all reality, so it's great. It goes up to 7, right? I think are the scores on the exam. 6 isn't. If you're like, I'm okay at math, I get like A's and B's most of the time. 6s and 7s are totally realistic. You just can't quit and give up. Okay? If you care about the score on this, those good scores are eminently doable. Eminently doable. The hardest piece is going to be just making sure you give yourself enough time to finish everything that you know how to do and not get bogged down on trying to figure something out that's you're not sure what to do with. Most of the questions are multiple parts. Most of the parts can be done independent of your previous work. So if you're not sure what to do, just skip it and go to the next thing and make sure you have a chance to do everything you know how to do. But if you take that kind of an approach, 5, 6, 7s are very realistic scores. If you're somebody that's in a diploma program student and kind of wants to do well on this because they might have something else that they're really going to struggle with, getting a 5 or a 6 on this course is pretty realistic, and I think can go a long way to helping you out on your diploma. If you get a 6 or a 7 somewhere, I think that makes everything way easier. Is that right?
Yeah. 12
Yeah. So if you can get a 6 or a 7 on this one, you can get a 3. I don't think you can get a 2 and get a diploma though.
You can get 1, 2.
You can get 1, 2? Okay. Well, then you need get a 7 here on this one if you're planning on getting a 2 somewhere else, because this is, if you study and you try, 6s and 7s are super doable. Especially because I don't think any of the diploma kids punted on their IA either. Your IAs, I think, your diploma program kids were pretty decent. So that's makes life much easier when you have a 6 or a 7 kind of already, or 5, 6, or 7 already booked on that.
6 or 7.
Well, 5, 6, or 7 if you already kind of got that score booked in there, because I think that's I think it's 20% or whatever.
Yeah.
So I think you did okay. But we'll show you I'll get you an old exam here after we finish chapter 11 that you can start looking through also.